let's take a moment to just look briefly at the other inverse trig functions. And we'll look for a moment at one particular example of the secant inverse x. And I've graphed it down here. The graph, well, this is, if you recall, the graph of secant x. And if you notice how we've described the range of our secant inverse function is a little bit strange. It goes from 0 to pi over 2 and then from pi to 3 pi over 2. And so why is that? Well, we can look here on the interval from 0 to pi over 2, we get this branch of the secant function that's in red here, and then on the other interval from pi to 3 pi over 2, we get this other branch. So between those two branches, we get essentially we hit every value that the secant function will take on. And moreover, those two pieces don't overlap horizontally, so they would, taken separately, define the secant function in a one-to-one way, so that it's so that we can do the inverse. And the choice of these two branches is a little bit different than the way that some other books might choose to do it. Some books might choose to do the interval from pi over 2 to pi instead of from pi to 3 pi over 2. But that's just a choice of the author, and I think it makes sense to do it this way, because what we'll see in a moment is by defining it this way, we've sort of simplified the formula for our derivative of the secant inverse function. And then you guys can also see that we've done something very similar with the cosecant function, which is essentially the same interval with excluding the left endpoints and including the right endpoints instead. Now, if I take a moment here to think about how we would derive the formula for the derivative of secant inverse, we can do it in a way that's sort of similar to how we've done it for the other ones. Take the definition that we've come up with, that y equals secant inverse of x if and only if x equals secant of y, and then find the derivative of y implicitly. And what we wind up with here is 1 equals the derivative of secant, which is secant y tangent y times y prime. So we get y prime would be 1 over secant y tangent y. Okay, now we've written it up here that secant of y is equal to x. We know that will be equal to x. How about tangent of y? So we've seen this formula before, that the identity that tan squared of y plus 1 is equal to secant squared. So if I isolate tangent here, we get tan squared y equals secant squared minus 1. And then when I take the square root, I get tan of y equals plus or minus the square root of secant squared minus 1. Okay, so now this is where that choice of our interval was important, because we've chose the interval in such a way that we've ensured that tangent is always positive. And so with that choice, now we can just stick with the positive square root of secant squared minus 1. So that was where the that choice of the interval was important here, because tan y is going to be positive for y in those intervals. If you remember, it was from 0 to pi over 2 and from pi to 3 pi over 2. And therefore here, finishing it up, we have 1 over secant y square root of secant squared minus 1. Leaves me with, now we can replace secant y with x. 1 over x square root of x squared minus 1. Okay, so the nice thing is that here, because of the way that we've defined the secant inverse function, this formula looks simpler than other cases where, had we chosen a different interval, we may have needed to use absolute values on x. But by the way we've done it here, we can just leave it without the absolute value. Okay, so that gives us one extra formula, and notice that we've discussed these formulas already. We're not going to mention how to get the derivative for cosecant inverse or for cotangent inverse, but you can easily notice that there is a similarity between each of these derivative formulas. For instance, if I look at the formula for the derivative of cosecant inverse, it's the opposite in sign of the derivative for secant inverse. Similarly, the derivative for cotangent inverse is the opposite in sign. It's the negative version of the derivative of tangent inverse. And we see that same with sine inverse and cosine inverse. They're opposite in sign. So with that relationship, we can easily remember these formulas. Essentially, there's three variations where the complementary one has a negative sign in front of it. So yeah, so let's just practice with these formulas a little bit. Suppose I want to differentiate the function y equals 1 over sine inverse of x. Now this is a good one to remind ourselves of the difference between the inverse notation and then the -1 power. So like if I write sine inverse of x, that's different than giving it a -1 power. Remember, 1 over something, you can write it with a -1 power. But the inverse here is a different notation. So it's good to remind ourselves how to distinguish between those two things. If I put the -1 power on the outside like this, it means it's 1 over that value. So when we compute y prime here, we can use that, this form like this. So it'll be -1 times sine inverse x to the -2 power. And then chain rule says I'm going to multiply by the derivative of sine inverse x, which we know. So 1 over the square root of 1 minus x squared. So we'll have -1 over, I'll put sine inverse x quantity squared here in the denominator, and square root of 1 minus x squared down there. And here in this next example, we've got the function x arctan of the square root of x. So when we do f prime, we're going to need to use the product rule. Okay, so we'll take the derivative of x, which is 1, times arctan x without taking a derivative, plus x times the derivative of arctan of the square root of x. So if you remember, arctan, the derivative of tan inverse, was 1 over 1 plus x squared. But in this case, we got the square root of x inside there. Okay, so there we're replacing x with the square root of x, and then with that we're going to multiply by the derivative of the square root of x. So there we're applying the chain rule. Okay, so we've done the product rule and also the chain rule there with that last part. So this simplifies a tiny bit. For instance, here I could do x divided by the square root of x down there. Leaves me with the square root of x in the numerator. And then let's see, the square root of x squared just becomes x. So I've got 2 times 1 plus x left over.